everyone, and welcome to CS10 Discussion 7. This week we'll be going over some recursion review and then midterm review since your midterm is coming up. So since we missed our discussion on recursion last week, I'm sure a lot of you are probably a little bit shaky about exactly how recursion works, and that's totally fine. So I'll just review real quick what recursion is and how we implement it in Snap. So with recursion, as Dan mentioned, there are two main parts. First we have the base case, and in the base case we have a problem that's simple enough to be solved directly. And then our second part is a recursive case, which has three primary components, and this is where we call the function within itself. So the key idea behind recursion is we're calling a function inside of itself. So the three components we have are, first, we divide the problem into smaller parts. And with every divide, we move towards our base case. So that doesn't mean literal arithmetic division. It just means that we're making the problem into smaller parts. So if you guys remember Fibonacci from last week, hopefully you guys watched the video. This is the part where we're subtracting by 1 in the recursive call. So we're doing n-1 and then calling factorial on that. And so that leads us into our next part of recursion, which is called invoke. And that's where we're invoking our function on the smaller parts. So this is our recursive call, where we're calling the function inside of itself, but we're calling it on smaller parts of our inputs. So that's where we were calling factorial of n-1. And then finally, the third part of our recursive case is called combine. And so that's where we're combining our solutions of the parts in order to get the bigger solution. So we're combining the solutions of the smaller parts. And for factorial, that would be where we multiply n by factorial of n-1.
And then...
Alright, thanks.
Okay.
No problem.
It started, right?
Yeah. Do whatever. I'll like cut shit
Okay.
later.
No, you can keep it in.
Shut up. Okay, so let's take a look at this fractal problem here, and it says write out code to draw the fractal below. The sprite starts out at the bottom left corner of the image facing right and ends in the position the sprite is in the picture.
The rectangle is always 2/3 of the length of the entire line, and 1/3 the height. Now we see that this is a recursive fractal problem. So every recursive problem has a base case and a recursive case. So in this example, let's talk about our base case first. So the simplest case would be when the level is equal to 1, so when n is equal to 1. Now for our base case, we see that all that's happening is that your sprite is moving a certain amount of steps. So if level is equal to 1, move size steps.
Okay, let's move on to the next case where level isn't equal to 1. And I think the easiest way to do fractal problems is to just move one step up to level equals 2 and slowly walk through that. So we see here that they've bolded out the parts where we need to call on fractal recursively. So these two parts will be making recursive calls, whereas in these two parts, we'll just be moving the sprite.
Yeah. So the first thing we're going to do in our else case is we're going to move a certain amount of steps. Now, if we look back at the problem, we see that the rectangle is always 2/3 of the length of the size, which means that if that's 2/3 of the size, then this first line would be 1/3 of the size. So move size divided by 3 steps. Afterwards, we're going to see that there's a change in orientation because we're moving upwards after that. So let's turn 90 degrees counterclockwise.
Cool, so now we've made it to our recursive case, and we see here that this line is just exactly what we drew for level equals 1, or n equals 1. So we can call fractal on level equals 1, or in other words, n-1, or level -1 levels. And the size, we see that in the problem that the rectangle is 1/3 the height, which means that this height here is 1/3 the height, the length of size. So when we call it, we will say fractal level -1, and then size is size divided by 3.
So now we're kind of up there, and we want to turn right again because we're facing upwards, but the next part, which is non-recursive, would be another motion. So first let's turn 90 degrees clockwise. And then we're going to move a certain amount of steps. In this case, we already see that we should move 2/3 the size of our input. So we're going to move 2 times size divided by 3 steps. Next, we're facing right, but we want to face downwards for the final part of this problem. So let's turn in 90 degrees again, clockwise.
And now we're at another recursive case, which we can see is recursive because it's bolded, and it's exactly the same as the first recursive call we made here. So we'll call exactly the same thing, fractal level on level -1 and size divided by 3.
Now we're almost done, except we need to change the orientation so that it's facing its original direction. This is especially important when we move on to higher levels of this problem. And we're done.
Hey y'all, welcome to, I guess, like the online version of CS10. And so I'm gonna be going over multiply and then exponent. So basically, the multiply function, it's a recursive function and we're trying to build multiply without actually calling the snap block that multiplies two things. So what is multiplication? Multiplication is just adding a number a set number of times. So in this case, we'd be adding 2 4 different times. And so when we look at this, it actually, a really interesting way to break this down is this is the same thing as doing 2 plus 2 times 3, and that's basically where our recursive case comes in. So first, whenever we do recursion, we always want to think about a base case. So what's the simplest thing we can multiply? We can multiply any number by 1. So in this case, if this was 2 times 1, we would just want to return 2. So whenever it's, y'all are gonna edit this, right?
Yep.
Whenever you're calling multiply on x and y, if y equals 1, we can just return x. Because that's the simplest case, that's gonna be our base case. So now whenever we think about our recursive case, we can basically take this example. So we have 2 plus 2 plus 2 plus 2. That's the same thing as 2 times 4. Which is also the same thing as 2 plus 2 times 3. But here's where the recursive leap of faith comes in. 2 times 3, we already have a function that does that. That's multiply. So this is the same thing as 2 plus multiply of 2 and 3. So using that same logic, we can build the recursive case. So we want to report x plus multiply because the only thing that changed from here between 2 to 4 is that we actually subtracted it by 1 and then added this number one more time. So that's basically the same logic that happens here. So in recursive cases, we all know that we have to divide, invoke, and combine. So this is actually where we would be dividing the problem. We're making it smaller and smaller until y eventually hits 1, ending like the recursive call. Then we invoke it by calling multiply again. That's what makes this recursive, is that we're calling multiply inside of its own function. And then we would be combining by using this plus. So that's how you do multiply recursively. Right.
So now we're going to do the exponent version of the same question. So basically we're going to find the exponent of, let's say 3, 4. Then basically what exponent does is it takes a number, multiplies the said number by these many times. So 3 to the power 4 is basically the same thing as 3 times 3 times 3 times 3. We can also write this as 3 times 3 to the power 3, because this would give me this entire thing, 3 times, right? So now this is basically the same function with 1 reduced. It's basically the same thing as multiply, but instead of adding stuff, we are multiplying it. So this could easier be written as right? Now this would give me this. This is where the leap of faith comes. This would give me this, right? We're just assuming it does. So now let's just actually start coding. First of all, what's the base case? So what's the easiest value where we could get like the answer right away? It's 1, right? Any number to the power of 1. So let's just say that we have exponent x comma y. So if y is 1, any number to the power 1 would just give me the number, right? Right? So now for the recursive case, if y is not 1, then what do you want to report? This structure, right? You want to do the same thing but with variables. So what's our 3 here? 3 is the first thing, right? So x. Now we are multiplying that by the exponent of 3 to the power 3, this thing. This function does the same thing, right? So and we are done. So here we are dividing the problem into smaller parts by reducing the value of y each time up until it reaches 1. Then we are invoking the recursive call by calling exponent inside the function definition right here. Sorry, not in the function, inside the function. And then we are combining it using this sign right here. You can go through it to like make sure it does work properly, but this would work because we are assuming this is correct because we have a right base case. That's the leap of faith. Thank you.
Hello! Let's talk about Fibonacci. Alright, so for those of you who haven't heard about Fibonacci before, it's a sequence of numbers where first you start off with two ones, so you start off with 1, 1, and then every subsequent number after that is the sum of the two numbers before it. So then to get the next number in the sequence, we have 1, 1, and that gives us 2. Cool. And then next, to get the next number, we'll add up the next two numbers. So now we have 1 and 2, and we'll add those up, and that gives us 3. And then this pattern continues, so we have 2 and 3, which gives us 5, 3 and 5, which gives us 8, 5, 8, 13, and then it just goes on for infinitely long. So then, notice how this question is sort of inherently recursive, right? We're using the previous solutions to build up the next solutions, and that's a frequent pattern that we see with recursion. So then, how do we put this into code? So let's try to number our Fibonacci sequence, right? So let's say, okay, 1 is the first number of the Fibonacci sequence, and then 1 is the second number, 2 is the third number, and then 4, 5, 6, and 7. All right, so now we've numbered off our Fibonacci numbers in our sequence. So let's say that this is some variable n, right, where we're trying to find the nth Fibonacci number. So n equals 1, 2, 3, 4, 5, and then so on and so forth. And so now to find the nth Fibonacci number, we just add up the previous two Fibonacci numbers, right? So let's say that n is equal to 3. In order to find the third Fibonacci number, then we just add up the previous two Fibonacci numbers. So we could say that this is at the position n minus 1 and the position n minus 2. So now if we were to write this out into an equation, then we would just say the nth Fibonacci number is just equal to the n minus 1th Fibonacci number plus the n minus 2th. So putting this in terms of divide, invoke, and combine, we can find all three of these parts inside of our equation. So first, let's start off with divide. Divide is where we're moving towards the base case. So we're reducing the problem into smaller subproblems. And so that would be this n minus 1 and n minus 2 part. So we're subtracting from n, and we're moving towards the base case to work on smaller subproblems. And then next we have invoke, and that's invoking our recursive call. So that's here where we're calling Fibonacci. And then finally we have combine, which is combining the results of the subproblems. And so that would be where we're adding up the results of the subproblems for Fibonacci. So we have divide, invoke, and finally combine. And so that will give us our recursive case.
All right, so the first thing we need to think about when we're creating our recursive function is what is the base case? What is the simplest possible input? So in the case of Fibonacci, that would be the first or the second Fibonacci numbers. So we're going to say if n is 1 or 2. And to make that simple, we'll just say if n is less than 3, which is the same as saying if n is equal to 1 or n is equal to 2. And we're going to assume that we won't be putting in any negative inputs for n. So if n is less than 3, then the Fibonacci number will just be 1, because the first and second Fibonacci numbers are just equal to 1. So in the base case, we'll just report 1. And that'll be our simplest possible case. And so now let's look at the recursive case. And this is pretty simple, right? We already have our equation. So that was just where we report Fibonacci of n minus 1 plus Fibonacci of n minus 2. And so that'll be our recursive call. So I'll have Fibonacci and we'll add it together. Go. Of n minus 1 and n minus 2. And so that is our Fibonacci function. So now let's try to figure out what the runtime of Fibonacci is. So in our base case, we only have one step for Fibonacci of 1 and Fibonacci of 2, right? Because after that, we just report 1. Then what happens in Fibonacci of 3? So in Fibonacci of 3, we need to figure Fibonacci of 1 and calculate Fibonacci of 2. So we'll nest that underneath Fib 3. All right, so now what about Fib 4, right? So inside of Fib 4, we need to calculate Fib 3 and Fib 2. And then how about underneath Fib 3? That's Fib 1 and Fib 2 again. So see, we're doing some redundant calculation here, right? I calculated Fib 2 once over here. Oops. Over here. And then I calculated it again here. So this is a highly inefficient function. Let's take a look at calculating Fibonacci of 5. So underneath here, we need to calculate Fibonacci of 4 and Fibonacci of 3. And then underneath, again, Fib 3 and Fib 2. So notice how the number of calls we're making here is quickly growing, right? With every new number we add, we double the number of calls we have to make to Fibonacci. And if you guys remember from our algorithmic complexity discussion, whenever you see this pattern of doubling runtimes or doubling number of steps, that's usually exponential runtime. So the runtime of Fibonacci is exponential, at least in the recursive way that we wrote it. If you were to write it iteratively or using memoization, then you would be able to have a linear runtime.
Hey there, welcome to Aaron's Corner of CS10 discussion. We're going to be doing the Mobile problem, which is the problem that starts out Little Town in Alabama. It's like on one of the last pages. Okay, so this problem is trying to find the total force that one mobile has. So here we're looking at 3 separate versions of a mobile. We have X, Y, and Z. And if you notice, each mobile is considered to be composed of smaller and smaller mobiles. So if you see, X is actually what we're going to call a simple mobile here. It just has one weight on it. But each of the other mobiles has sub-mobiles too. So for example, Y is composed of 2 simple mobiles, one with a 3 weight and one with another 3 weight. And then Z would be a little bit more complex. It's got a mobile on the right, mobile on the left. Or sorry, yeah, but you get what I'm saying. And the one on the right is also complex. Okay, so we want to use the recursive structure of the mobile to solve the problem of what is the total force of this mobile recursively. Okay, so first of all, let's think to ourselves, what we want is the total force of this. So we tell you that you can write down force technically as mass times the constant for gravity. And the constant for gravity we're just going to say is a given. So we got that. And then for the mass of a certain mobile, well, we're going to give you a block that gives you the mass of any given one. So for example, if we're trying to find the mass of this, can you see it? Great. That guy is going to return 6. Right? Okay. Awesome. So if we're writing a recursive function, what's the first thing we have to think of? The base case, right? So for this problem, we're going to ask ourselves, what would be considered the simplest form of the problem? What can I write this function that checks for a simple form and just gives me a number right away? Well, turns out that if we have just one simple mobile left, finding the force of that is equivalent to just finding the mass of that simple mobile and multiplying it by the gravity constant, right? There's no sub parts to break this problem into. We know we can just give you the force right away if it's a simple mobile because there's only one weight to calculate. So we can say we just need the mass of this of a simple mobile times big G. I'm going to call the gravity constant G. Oh, but how do we know that it's at the base case? Well, we give you a block to check to see if it's a simple mobile, right? Awesome. So if it's a simple mobile, we're going to hit that. And then otherwise, what? Well, otherwise, we have a more complex mobile that we need to break down into its parts. So how do we find the total force of each part of the mobile? Well, you have a function that does that. And it's called force, right? Yeah. So all I need to do now is find the force of each component part. Well, what parts are those? You got a left part, right? And then you got the force of the right part. And there you go. Now I'm going to switch it over to a screen capture and I'll show you what this would look like written in code.
Hello, welcome to virtual discussion. You're in Mertz's corner now. As you can see, I have much less energy than everyone else, and my beard is in an unruly state, so I apologize. But we'll be going over one of my favorite questions in CS10. Not my favorite, but one of my favorites. Path home. Please have it open next to you on your screen somewhere as I go over this. It'll be extremely helpful. So the goal of this question is, it's saying we have this forest-like thing, a tree structure. This is home. We want to know if we start at a certain place here, is there a way to get home? For example, here there clearly is. If you start at 7, you just go here and you get home. But if you start at 5, there's no way to get home. In order to be able to figure this out, we need to understand what our helper blocks are doing very well. We have a few. We have home, we have dead end, we have go left, and go right. And each of these takes in a place. Now, what do each of them do? Home takes in a place and tells you if the place you're at right now is already home. Dead end tells you if the place you're at right now is a dead end. And go right will take you from the place you're currently at to the place on the right. Go left will take you from the place you're currently at to the place to the left. So, we want to write this recursively. If we're going to write something recursively, we need a base case. What is the simplest possible thing that could happen in one of these? You could start at home, right? If you start at home, then you don't have to do any more work. So that'll be our base case when we write this. Path, home, place. So if place is our variable, if home place, we can just report true because we know there's a way to get home because we're already home. Now, what is another simple case? If you're at a dead end, say you're over here, and there's nowhere to go, can you possibly get home? No, you can't. So that's the second case. If dead end place, we report false because there's no possible way that you could get home. However, someone might ask, why did we do the recursive or the base cases in this particular order? Well, imagine if dead end place was first, you wouldn't always be correct because if home wasn't 6, for example, and home was 4, you are home here. However, it's also a dead end. But you don't want to report false because there is a way to get home since you're already home. So you need to check for home first. But now we get to the more interesting part, the recursive case. There's a key idea that we need to use in this problem, and it's called the recursive leap of faith, which you've heard multiple times today. And the idea is you don't want to start thinking about, okay, I'm going to be here and then I can get over there and this and can I go blah, 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 blah. You want to take things one step at a time and then let your function do the work for you. So, to know if you're starting here, there's only 2 possible things you can do. You can either go right or you can go to the left, right? So let's at least write those things down here, because you know at some point you're either going to go right or left. We don't know what we're going to do with that yet, but we can say go right place and go left place. What do we want to know about each of these, right? Recursion, divide, invoke, combine. We've divided our problem into the right half and the left half. Now we get to the invoke step. We take the leap of faith and we say, okay, once I go to the right, all I want to know is, can I get home from that place? So do we have a function that takes it in a place and tells us if you can get home from that place? We do have a function that does that. It's the one we're writing. So we can say, we can call path home on go right place and on go left place. That is the leap of faith, because essentially you just want to know, hey, if I start at a certain place, I can either go right or I can go left. From either of those places, can I get home? And you call your recursive function in order to do that. Now, the final thing is the combine step. There's a path home if either of these reports true, right? Because there's only one home. So we want to combine these two, which both return Boolean values, so that if either one of them is true, the whole thing returns true. Which operator does that? OR. So you combine this whole thing in one giant, I can't draw hexagons, one giant OR, and that's Patricia laughing in the background at my poor drawing skills. Yeah, you call OR on your whole function, and then you're done. So that's path home place. I highly recommend you try solving it again on your own once until you really understand what's happening and why we can use the recursive leap of faith.
Was it good?